Say you're driving a car, and if you make a really sharp turn, the curvature value is going to be bigger. If you make a softer turn, it's a bigger circle, and K value is going to be smaller. That's all. Just like the slope. Remember when you talk about slope in cut 1, slope M is equal to what? dy over dx, and you got what? Changing of the y, rise over change of run, right? You have the slope, and that value will tell you how steep the line is, right? If M is big, the line step up pretty fast. M is small number, go up a little. If M is negative number, the line is going down. And K here is also another number, very similar, pretty similar to the slope. They tell you what, say you have a curve, right? Curvature right here, gonna be bigger than curvature right there, because here you make a sharper turn, and this one you make a softer one. It's sharper right here, it's softer right there. Okay. And this one's always a positive number, so we put the absolute value into it. Right? So it doesn't have the negative value like the slope, always positive. This is the definition, and we have a problem with the definition. It's very hard to apply to our calculation. So we're gonna modify the formula a little bit, and we have a theorem. And actually, you guys can use this formula. K is equal to T prime, derivative of the tangent, this is tangent, okay, over derivative of the vector r. You guys see how we get from here to here? We divide both top and bottom by dt. So d big T over d small t over ds over dt. Okay? This is what? Derivative of unit tangent vector. And ds over dt is the tangent vector, or derivative of r. R is this. Same thing. Okay? And that is a formulas that a lot of people use in here. The derivative of unit tangent vector over the derivative of the function vector function. And don't forget the absolute value, okay? It's going to be a number, a positive number. We also have a couple more formulas for you guys, pretty useful for you guys to calculate the curvature. And this is another one using the cross product. K is equal to R prime cross R double prime divided by R prime cube, I think, magnitude. Let me double check. Yes, it's right. And same, it's going to be a positive number, so I better put absolute value everywhere. The cross product of R prime cross R double prime. See, remember you got a vector R, you calculate R prime, you calculate R double prime, you cross them, you find the magnitude, and you find the magnitude of R prime, put it in there, you have curvature. Okay. And in two-dimensional space, this is a short version of this one. Say the variable is x, right? Whatever the x is, this is variable t. I'm just omitting it. T in here, t there, and t there. Okay. In short, I usually don't write t, but hopefully that's not confusing. But same thing in here. 2D is what? F of x. Okay. Y equals to f of x. Then the formula is this: f double prime of x over 1 plus f prime t square, take square root, and then everything raised to the third power. Oh, how about, let me write this way, raised to the power of 3/2, okay? Square root means 1/2, so everything raised to the power of 3/2. Same thing. Okay? You have 3D. Means what? You have a curve in two-dimensional space, and you want to calculate curvature at the point x somewhere, and what? Apply this formula. You would have the answer. And the proof all those formulas are in the book, so please look it up by yourself. Okay, so let me summarize what we just learned so far. So far you have a curve, okay, 2D or 3D, doesn't matter, R, T. And then if you take derivative, this is called the tangent vector. So here's the point right here, tangent vector, okay? And you define the unit tangent vector by normalizes to make what? R prime divided by the magnitude. So R prime of T divided by the magnitude of R. You have the unit tangent vector. Okay, another point. T. All right. What if you take derivative of that function t, t prime? You're going to have something perpendicular. There's another vector that's perpendicular to vector t right here, unit tangent vector. And again, you want to normalize it, make it the vector with magnitude equal to 1. You define something called the normal vector. Okay, define the normal vector. This is derivative. You're going to have this vector, right? But the length may be shorter, may be longer than 1, and we don't like to work with those who only work with vector with length 1. So we define something called normal vector, denoted by vector n. Is t prime and divided by the magnitude of t prime. So this vector n, not just perpendicular to vector t, but it also have the length of 1 unit, and this is called the normal vector. All right. Now we have two vectors. What we can do is we can cross product two vectors. So we have t first. We have vector t. If we cross with vector n, keep in mind that t is a unit vector. All right. Vector with length 1. N is also another unit vector, and t comes first. T cross n we define as a vector b. B is called a binormal vector. And like what we learned before, for the cross product, vector b will be perpendicular to both n and t. Okay, t and n. So if you got, say, t right here, okay, and then n right here, both unit vector, and b going to be up here. Perpendicular. Okay. They're all perpendicular. Using the right hand thumb rules, t go to n, you have b come up. All right. Let me see if I missed anything. Before I move on to the last section, let me just go over an example, give you guys an example to show you the calculation you have on what we learned up to now. I'm going to use the same old example, and it works for any kind of example. Got to do something easy enough so we don't have to do a lot of calculation. Just try to demonstrate the formula. So RT is equal to cosine T, sine T, and then T. And this is the helix. Okay? The graphs will look like this, like a swing. Right. So R prime T is going to be negative sine T, cosine T, and 1. Right? Derivative cosine is negative sine, derivative sine is cosine, derivative T is 1. Okay? So the magnitude of R prime is square root of sine square T plus cosine square T plus 1. You know the sine square plus cosine square is 1, so 1 plus 1 is 2. Magnitude is square root of 2. Okay? And this is the tangent vector. but the magnitude is square root of 2. It's not unit. So we're going to calculate the unit tangent vector. Is r prime over magnitude of r prime, which is 1 over square root of 2 magnitude, and what? Negative sine t, comma cosine t, comma 1. Okay, and this is the tangent vector. All right. Now you have tangent vectors. Can you calculate the derivative of this? T prime is 1 over square root of 2 constant. I'll leave it out there. Derivative of sine, negative sine is negative cosine. Derivative of cosine is negative sine. Derivative of 1 is 0. And this is the derivative of the tangent vector, unit tangent vector. Can I calculate the magnitude of this? It's 1, right? Of course. T is 1 right here, derivative. Take derivative of this. Square root of cosine square t plus sine square t plus 0, and this is equal to 1. Okay. So can you calculate the normal vector? The normal vector is t prime over the magnitude of t prime magnitude of t prime is 1 already. We're lucky. So t prime is what? Negative cosine of t, comma, negative sine of t, comma 0. Okay? Now that you have the unit tangent vector, you have the unit normal vector, you cross them, you're going to have the binormal vector. Okay? Now let me write down here. I'm running out of space. Let me erase this. I have the normal vector in here. It's equal to what? Negative cosine t, comma negative sine t, comma 0. I got 2 vectors already. So vector B is t cross n. And you know how to do cross product, right? Well, the I term is what? 0 times cosine with 0 minus plus. It's going to be sine t. And then for the, this is the I, J, and then the K term. The I term, I'm going to do what? 0 times cosine and minus negative sine times 1. And then for the J term, it's 0 times negative sine with 0 and minus cosine times 1, which is positive. But we change the sign of K, J, so it becomes minus cosine of T. And then for the K term, sine square minus minus become plus cosine square, so it's going to be 1. Okay. All 3 vectors, B, T, and N, are going to be perpendicular to each other pairwise. Okay? And what about the curvature? I can use one of the formula to calculate the curvature. And curvature, K, can be calculated as what? What did I have? Can I calculate T prime? Magnitude over r prime magnitude. Double check for the formula, see if I'm right. Yeah. And what is t prime? Oh boy, I just erased it. T prime magnitude was 1, right? Okay, and then r prime is 1 over square root of 2, so this is 1 over square root of 2. So the curvature of that thing is a constant. Is what you see the ellipse right here. At every single point of that spring, the curvature is the same because what, it keep rotating, keep turning with the same curve. Okay, with the same shape. It's never change. It's a constant curvature. And this is the end of 13.3. Before I move on, let me double check on my notes, see if I missed any material that I want you guys to know. Pretty good. Okay, now, last section, I'm going to show you an application in physics. for vectors functions. So pretty much I'm repeating 13.3, but you have something called velocity, acceleration, right? Physics. You know that vector r in math it's just a vector function. In physics they call it what? The I think it's called the position function, right? Yeah, the position function is saying xt, comma yt, comma zt. Nothing new. And now in physics, t stands for time. Okay, so it's going to be from 0 to infinity. When time changes, and the position of the particle is going to change. We have a curve. Just draw it randomly. So t equal to 0 is right here. T equal to 1 is right there, and t equal to 2 is right there. Okay. Where x coordinate is a function with respect to the time t, y coordinate is another function with time t, and z coordinate is another function with time t. And this is a vector function, a particle on the three-dimensional space. And of course, you have two-dimensional space, and z is equal to 0. You got just x and y. Same thing. And you have something called derivative, right? R prime, which is x prime. I'm getting lazy, so let me just write x prime, y prime, and z prime. Okay, I mean what? X prime of t, y prime of t, and z prime of t. All right. And in physics, this is called vector v. And v stands for the velocity. Okay. And then the speed is the magnitude of the velocity. How fast the particle moves at that moment. Okay. And velocity here tell you two things. The speed means what? The magnitude and the direction. Okay. So vector v actually implies two things. The speed and the direction. Okay. Speed is just the magnitude of the vector. And now you take the derivative of the velocity. So r double prime of t, which is v prime of t. Now we call it what? Vector A. And for those who study physics already, you know this is called what? The acceleration vector. Okay? So at a point somewhere, we know the speed, we know the velocity vector, and we also know the acceleration means what? How fast the speed is going to change. How fast the velocity is going to change. Okay? So, I'd like to draw something simple. Have a curve. Okay? At a point, velocity, right? Acceleration, somewhere say pointing this way, acceleration. Okay, now a little bit more about acceleration. The vector of acceleration may point anywhere in other plane, and we're going to break the acceleration out into the two components. The right. Called the tangential components, tangent to the curve, and the normal components is going to be perpendicular. I tried to draw it. This is 3D, okay? So you have to imagine it's 3D, so it's perpendicular. Right. This is called the tangent components of the acceleration, and this part right here is called the normal components of the acceleration. So there are two parts of the acceleration vector. The one changing the speed, all right, along the tangent line, and the one changing the curvature. All right, and you know what? AT is really, let me make sure that I copy it right. Is V prime. And AN, they use capital T. And AN is curvature times velocity squared, I think. to explain to you what is V right here. So this, okay, we use a little bit different notation. It says that V, right? Where vector V is equal to R prime, right? Vector V is equal to R prime of T, and then the V right here, not normal vector, is the magnitude of the vector V. Okay. So if you don't want to write this way, and then V prime is the derivative of this thing. Okay. This is a function really. Is the derivative of this one. Vt derivative. Okay. So this is what the speed function, the function of the speed will tell you what, how fast the particle is moving, right? And then you take the derivative of the speed, you have the tangential acceleration. And you take k times the speed squared. K here stands for curvature. We have it before, okay? You have the normal tangent. All right. I'm not sure how much physics we have for each of you guys. So I'll just provide the basic ones that the book gives you. Of course, the more basic, the more physics you have, the easier for you guys to see the stuff. I bet many of you guys take calculus and physics at the same time. You guys will see two things at the same time. Okay. See if I missed any formula. Oh yeah, last one. And the book just provided to you. So there is a proof in the book. Let me just throw out a formula. All you need is the formula to do the work. The tangent part of the acceleration. This is a number, okay? It's equal to the dot product. So where's the dot product in here? Make sure that I got it right. Yeah. R prime dot R double prime over R prime magnitude. Okay? And the normal part, AN, is R prime cross R double prime divided by R prime. So the only difference, this is dot and this is the cross product. Okay? No numbers. Here's a curve. It's a point in here, okay? And RT is the function for the curve. R prime T will give you what? The tangent vector, okay? Which is the velocity. Okay? Tangent vector. And you want to calculate the unit tangent vector. We learned this already. We know what? R prime T over magnitude of R prime T, which is Vt over the magnitude of, this is vector, okay? R prime T. I just tried to write a little bit more in the book, but it's the same. Okay, and after having the velocity vector, you take the derivative, you have the acceleration vector. At is equal to what? V prime T. Okay. And the acceleration vector, I'll just randomly choose right here. Can be broken down as two components, the tangent components and the this is AT right here, and the normal component. This is AN. This is this part right here. The length right here is AT. AT. This length right here is AN, okay? So AN is the length, okay? So AT can be written as what? Acceleration with respect to velocity going to be the tangential part times what is that right here going to be vector T plus AN times vector N, okay? Keep in mind that T and N are both unit vectors, so it's what? This is like the components, right? And then the magnitude times the unit vector. You have vector right here. This vector from here to here is AT times vector T. vector right here. AN is the length, okay? And then AN times vector T will give you the vector from here to here. T is the unit vector times the magnitude. You have this. And then, oh, I'm sorry, this is N. Okay? And then T is the unit vector times AT, which is the length right here. You have the tangential part of the vector acceleration. That's what they call it in physics. Okay? And I claim that in chapter 13 right here, the calculation of one problem may be long, but they all follow the formulas. So technically it should not be hard. One thing that I urge you guys to pay close attention to is your calculation, because you see there's a lot of work in here. You mess up with one number, or you take derivative one derivative wrong, then the whole calculation may be very tough. But all the problems in our textbook, they carefully choose the number so that if you follow all the steps correctly and you calculate your math correctly, then it turns out what the final solution should not be too hard. Okay? And this is all about chapter 13. Since I don't have any question directly from you guys using in class, and you guys can ask me a question, I can answer, I can explain more. But due to the circumstance that we have very special this semester, our classes are online, so I have to deliver the lecture via video clip. So just me, myself talking to the camera. So all I'm giving you on the board, and I'm expecting you guys to ask questions if you have any, or feel free to read the books, and then any part that you don't quite get, please email and ask. Okay? Let me stop the clip for chapter 13 right here. Thank you very much for watching. Any question, please ask one more time. And you guys have a great day. Bye-bye.